So thermochemistry is the study of the relationships between chemistry and energy. And so we're going to have to learn a little bit of physics here and define some words. So energy is the capacity to do work. It doesn't mean that you're actually doing work, but it means that you have the ability or the capacity to do work. So then we have to define work. What is work? Work is a force acting over a distance. So if I take my Apple Pencil and I push it across the bench, I did work. I applied a force and I moved it through a distance. So that's different than what we talk about as work more culturally. This is the scientific definition. Heat is a flow of energy. It's energy moving from one thing to another, and that movement is caused by a difference in temperature. So energy can be exchanged between objects through contact. And heat is one way that energy is transferred. So if you hold a hot cup of coffee, you feel the warm cup, right? Your hand is warming up because of its contact with the coffee cup. There's energy that is flowing from the coffee to your hand because your hand is at a lower temperature than the coffee. And we'll be talking about these sorts of things. So it's helpful to think of energy as a quantity that an object or a group of objects can possess, that can have. So I think money is a good analogy for energy. You can have money, and you can also transfer money to someone else, right? So energy is a lot like money. It's something that an object has. Here we have an illustration of a billiard ball rolling across the table. This has energy due to its motion. Then we have heat and work, and those are ways that an object can transfer energy. So you can't have heat. You can't have work. Work is a transfer of energy. Heat is a transfer of energy. So with the money analogy, that would be like paying someone for a service. Is transferring money to someone else. When the ball that's in motion here hits the other ball, it does work on that ball. It transfers energy to the purple ball, and the purple ball goes rolling off. And now the purple ball has the energy, and the white ball lost the energy. The energy was transferred from one ball to the other through work. There's no temperature difference happening here, but there was a force acting through a distance. So energy can move into an object or it can move out of an object, just like money can move into your bank account or out of your bank account, right? There are many different types of energy. There are two broad categories: kinetic energy and potential energy. So kinetic energy, the word kinetic should make you think of motion. Kinetic energy is the energy of motion. So we think about a ball flying through the air, or a train, going northwest at 55 miles an hour in one of those weird algebra problems, right? That's something moving. There's also thermal energy, which is a form of kinetic energy. It is an energy of movement, but not in the same way that a ball is moving through the air. It's the movement of the particles inside that substance. So I've talked about the gas, liquid, and solid states of students, right? So right now, the students in the class are in the solid state. You're sitting on stools at benches, right? Is everyone absolutely still? No. No one is absolutely still, because all of you, last time I checked, are still breathing, right? So at least there's that little bit of movement that you're breathing. Now, could you move more and still stay in your chair? Sure. You could get really, really fidgety. You could bounce your legs and tap your pencil and wave your arms around. That would be more energy. That is kinetic energy, energy of motion, even though you're not moving relative to anything else. Does that make sense? That's thermal energy. And thermal energy is associated with the temperature of an object. So an object that's warmer, the particles are moving more. Not necessarily relative to each other, but they're just a lot more agitated. And that's the temperature. Then we have potential energy, which is stored energy. As the name suggests, it's the potential for something to happen. And this energy can be associated with composition or with position of an object. So a ball raised above a table, or like this Sharpie marker raised above the floor, has potential energy. Because when I let go of it, something's going to happen, right? Falls to the floor. Because gravity's pulling on it. It had potential energy because it was elevated above a surface, and when I let go, the potential energy transforms into kinetic energy as it moves faster and faster down to hit the floor. So that's a positional form of potential energy. Chemical energy is a form of potential energy. And this is associated with the composition of the substance, and more specifically with the relative positions of the electrons and the nuclei inside the atoms and molecules. And so some substances like gasoline have a lot of chemical energy. If you do the right thing to them, they can release a lot of energy. So TNT, dynamite, lots of stored chemical energy, right? You ignite that, and that energy releases suddenly, and it's kaboom, right? Lots of energy. So some compounds like TNT or gasoline are like compressed springs. They have a lot of potential energy that can be released, and it's released in a chemical reaction. So here we have sort of a flowchart diagram of these different kinds of energy. So energy, the capacity to do work, kinetic or potential, and then the ones that we are most interested in chemistry are thermal energy and chemical energy. So the law of conservation of energy states that energy can neither be created nor destroyed. This is a lot like the law of conservation of mass. Energy can be transferred from one object to another. It can take different forms, but you can't create more energy and you can't destroy energy. You can only shift it around. Just like as a regular citizen of the United States, you cannot create money, right? You can't create money. I suppose you could destroy it, but nobody wants to do that. Analogies can be taken too far. So here we have a person holding a ball above the table. It has gravitational potential energy due to its position elevated above a surface. When the ball is released, the ball begins moving downward, and it gets faster and faster as it gets lower and lower. So here its potential energy is at a maximum, and as it goes down, the potential energy decreases until it's at a minimum when it is on the table. As the potential energy decreases, the kinetic energy increases. And so it's transferred from one form to another. So think about this the next time you swing on a swing, right? At a playground or something, you swing on a swing. Like, I'm transforming potential energy, kinetic energy, potential energy, kinetic energy, potential. Yeah, that's what chemists think about. Yes?
Is the potential energy completely gone when it's on the table?
No. The potential energy is not completely gone. Because what if you pulled the table out from under the ball? Right? One of the things that's difficult about energy is, what do you call zero? It's a little bit like the temperature conundrum. You know, it's like, well, we can say that zero is the freezing point of water, but it turns out there's actually a lower one, and so we've established the absolute zero. But what's zero energy? Is that a substance that's not that's at 0 Kelvin. But if it was elevated above the surface of the Earth, it would have potential energy, so that wouldn't be 0 energy. And then if you're on the Earth, you're actually moving. So, speed relative to what? Relative to the Earth, you can be still, but the Earth is rotating, so you're going at, who knows, somebody probably knows, how many miles per hour? 500? 500 miles per hour as the Earth is spinning. We don't notice that because everything else around us is moving also. And the Earth is going around the sun, and so we're actually moving all over the place. What?
And the galaxy.
Yeah, and the galaxy's moving too. And so what's a stationary position? It's all relative, right? And so that's kind of what happens with energy too. And so instead of worrying about where is 0, what we end up doing is we end up talking about changes. So we can look at where it started and where it ended and the change in the energy, and we're not going to be concerned about with an absolute value of the energy.
Okay. So like when you said it was minimal at the table, that's just like relative to the table because we're just talking about
It's at a minimum for what happened right here.
Okay.
Yeah, so this was the maximum in this illustration, and it got to a minimum when it stopped at the table. And then you could say, well, it stopped at the table and now it's not moving anymore. Where did the energy go? Well, when the collision happens, but the table can't move away, the particles inside the table and some of the particles in the ball as well do a lot of vibrating and oscillating, and so the temperature actually increases. And so that energy that was potential energy turned into kinetic energy is dissipated as thermal energy. So here's an illustration with a spring. If you press down on this spring, you're putting mechanical potential energy into this spring. You release the ball and the potential energy is released and it's transferred into kinetic energy and the ball goes flying up in the air. So when we look at the exchange of energy, we have to define the two parties in the transfer. So like when we're dealing with money, if I'm buying something from someone, we can say, well, I'm the purchaser and they're the seller and I'm giving the money to this person, right? With the energy, we're looking at what the energy was in and where it went, but what we're doing is we're going to divide the universe into two pieces. The part that we're interested in we'll call the system, and the surroundings is the rest of the universe. Most of the time, the only surroundings that we're interested in are the ones nearby, but technically it's the rest of the universe. So the system is defined as the material or process that's being studied. So if we looked at the hand warmer example, we're looking at the iron reacting inside the hand warmer as our system. The surroundings is everything with which that can exchange energy. So the immediate surroundings would be your hand, the glove, the air in the glove, and even the air outside the glove. But technically it's the rest of the universe. This reaction occurring in a hand warmer is probably not going to affect the temperature of the air in San Francisco because that's too far away. But we just say the rest of the universe so that we don't have to draw lines of where we're going to stop, right? So the system and the surroundings. The system's what we're interested in, the surroundings is everything else. So conservation of energy means that the energy gained or lost by the system has to be equal to the energy lost or gained by the surroundings. Like with money, if I give you $5, I have lost $5, you've gained $5, no money was created or destroyed in that transition, right? So we can look at energy gauges here, like gas gauges in a car. So here's the system energy gauge, and it's half full before this transfer occurs, and here's the surroundings, everything else, and this is a quarter full. And so in the process of energy transfer, some energy is transferred from the system to the surroundings. And so now the system is a quarter full and the surroundings is half full. Because the energy that's lost by the system is gained by the surroundings.
Are we usually, is the system usually going to be what loses the energy?
No, the system may gain or lose.
Okay.
Yep. But the total amount of energy is constant. Make sure I didn't skip anything. So measuring energy, of course, we need units, right? Well, kinetic energy can be defined using this equation. Ke for kinetic energy is 1/2 the mass of an object times its velocity squared. This is really good for like trains, going at 60 miles an hour or whatever. You look at the mass of the train and its velocity and calculate kinetic energy that way. So from that definition, we can use units for mass and velocity to come up with a unit for energy. So in the SI system, the unit for mass is a kilogram. And for velocity, it would be distance divided by time, and the base units are meters and seconds. So meters divided by seconds, meters per second. And so if we take the velocity squared, we get meters squared per second squared. So 1 kilogram meter squared per second squared. Now that's a messy unit. So we gave it a name, we called it a joule. Joule. Capital J is the abbreviation. This is a relatively small unit. A 10-watt light bulb uses 36,000 joules in 1 hour. A lot of joules, but the joules are really small. So it's a small unit, it's a metric unit, and so we can use metric prefixes, and we often do. So a kilojoule is 1,000 joules. Any questions? I will not test you on the spelling of joule. Another unit that we use a lot in chemistry is the calorie, and you've probably heard of calories. But there are 2 different kinds of calories. The scientific calorie has a lowercase c, and its abbreviation is CAL. This was originally defined as the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. Well, that's kind of strange. Well, if you have no zero for energy and you're trying to define an amount of energy, how do you do that? How do you do that back in, say, the 1700s where you don't have electricity or anything and no technology? You have to come up, they were very, very creative. So 1 gram of water and the temperature's going up 1 degree, that amount of energy is called a calorie. So a calorie is a little bit bigger than a joule. A calorie is 4.184 joules, and this is an exact relationship. You don't need to memorize that. And then there's the calorie that we're familiar with, they see on the commercials and stuff. That's the nutritional calorie. That has a capital C. Now, they don't worry about that in regular society. But in chemistry class, the capital C here and the lowercase c there are very different units. They differ by a factor of 1,000. This nutritional calorie is actually a kilocalorie. Come on, pointer. A kilocalorie, 1,000 small calories. So small c, small calorie. Big C, big calorie. This could show up on an exam where it's saying that this candy bar has, 500 calories. It's got a capital C, and it wants to know how many joules of energy you could get by digesting that. The capital C is not a typo. Okay? There are occasional typos on the exam, but these sorts of things are always right. And if you're not sure, you can come and ask me. So watch out for big C's and little c's. Another unit is a kilowatt hour. That's what PG&E uses to measure electricity. That's abbreviated K capital D W H. We're really not going to do anything with that, but that's something you run into if you actually read your PG&E bill. You'd see that. So table 7.1 gives relationships between the different energy units. And the only thing that you need to commit to memory is you should know a kilocalorie is 1,000 calories. That's just knowing what kilo means. So you already know that. And then the big calorie compared to the small calorie, the big calorie is 1,000 calories. But the 4.184 joules is 1 calorie. I'll give that to you. This kilowatt hour one could show up in a homework problem, but I won't use that on an exam most likely. And if I do, I'll give it to you. And then table 7.2 is kind of interesting, but we're behind in lecture, so I'm not going to go over that. Just shows you amount of energy used in different processes in different units.